Okay, so now we continue with density functional theory. This is part 2 in the series on density functional theory, and here we are going to look at a kind of early version of density functional theory, which is called Thomas-Fermi theory. You will find a lot of the material I'm talking about in the book by Parr and Yang. Now, Thomas-Fermi theory. Okay, let's just start with it. So, rather than start with the derivation, I'm going to show you the final result and then we'll go backwards. What Thomas and Fermi were able to do, I think this was in the 1930s, but I have the dates in front, was to write down an energy functional. So this is the energy functional. It is a functional of the density. It's written in terms of a kinetic energy part, T of rho, an electron part, J of rho, and the external potential given by this integral over the density times the external potential, which is our electron nuclear interactions. T of rho is written as a constant times the integral of the density to the 5/3 integrated over all space. The electron term is simply the classical electron Coulomb interaction. It's repulsive, so it's a half the integral over rho times rho of R1, rho of R2 divided by R1 minus R2 dr1 dr2. And if you remember your electromagnetic theory, this integral here is simply the classical repulsion between two charge densities. And then we have the integral over the density times the external potential. Now this is a density functional. The only terms appearing in here are the densities, and if you put in the exact, you can then minimize this functional with variations in the density, and you will then be able to find the optimal density for this functional. So what's wrong with this? Why can't we use it? Well, we will see this in a few minutes, but this is intrinsically an approximate functional. Now, it can be improved. It has been improved by Dirac and then by Weizsäcker, but it remained an approximate functional. First of all, let's see how this functional was derived, because we're going to use some of the ideas in this derivation to try and understand how to make what we're going to see now is the Kohn-Sham density functionals. So let's go backwards and let's just start the slides into presentation mode and go back. Alright, so here we are. So this is now 1927 when Enrico Fermi and Thomas, I can never pronounce his name, Loew, I'm not going to try it, I think he's Welsh, Thomas, they derived the first true density functional. And in 1928, Paul Adrian Maurice Dirac modifies it to get what's Thomas-Fermi Dirac theory, and he includes the exchange interaction into this functional. Now, in order to see what Thomas and Fermi did, there are many ways of approaching this. The way we are going to do it is through what's called uniform scaling of the electronic coordinates. Now, this is something I have already put up a video and some derivations of what uniform scaling means, does. Well, so you need to have a look at that before going forward. This is what we're going to do in brief. What we're going to do by uniform scaling, what we mean is that we take the electronic coordinates Ri and we scale them all by a constant alpha. Now, alpha is non-zero, obviously. It's also a positive quantity. Okay. And what we had showed in those lecture notes is that under uniform scaling, the wave function psi goes to psi alpha of Ri, and psi alpha of Ri was defined to be alpha to the 3n/2 times psi alpha Ri. Now, wherever you see an alpha Ri, it means that all the electronic coordinates are scaled by alpha. Okay. Now you might say, what about, is there a sum over Ri? Well, so psi is a function of R1, R2, R3, etc. all the way to Rn. So psi of alpha Ri would be psi of alpha times R1, comma, alpha times R2, comma, etc. all the way to alpha times Rn. Now if you wanted to include the spin coordinates, they would also be included in there, but they would not be scaled. That doesn't make any sense, scaling a spin coordinate. It's only the spatial coordinates are being scaled. What about the nuclear coordinates? They are not scaled. Okay, now in my earlier lecture notes I've shown you why this choice of psi alpha leads to a fully normalized psi alpha for any choice of alpha, so that's why we use it. And we also showed this result here, and I'd like you to go back and show it for yourself, is that if psi alpha is defined to be as shown here, then rho alpha, the density that arises from psi alpha, will be given by alpha cubed times rho of alpha times r. Now we also proved these identities. We also showed that the kinetic energy evaluated with psi alpha was alpha squared times the kinetic energy evaluated by psi. We also showed that the electron, if this should have been V external, my apologies. So the external potential, and the R is kind of like my collective nuclear coordinates. If we took the expectation value of this external potential with psi alpha, we would get alpha times psi, this external potential with the nuclear coordinates now scaled, times psi. And the reason that we get a scaling function here and not here is that we haven't scaled our nuclear coordinates in this transformation. Alright. Now I've already proved this result, so I'm going to go through this rather quickly, but let's have a look at the first of these results. So we want to show that the kinetic energy evaluated with psi alpha gives us alpha squared times the kinetic energy evaluated with psi. So we start off by putting psi alpha on both sides of the kinetic energy. So this is psi alpha, just to remind you, it's given by alpha raised to the power of 3n over 2 times psi of alpha ri. So that you get a 3n over 2 from both psi star and psi, that gives you alpha to the 3n. The integral over psi star alpha ri, the kinetic energy operator for all the n electrons, so there's a sum here over I, and then psi alpha ri. The product here of dri just tells us that we are integrating over all electrons. Now once again, I should have a spin integral in here. I don't have it because we are kind of assuming that we can perform the spin integrals, and it just avoids some mess on these slides. Okay, now what we're going to do is make a few coordinate transformations. Take the alpha to the 3n and absorb it into the d alpha ri. Remember, each ri here is describing a position in three-dimensional space. So there's x, y, and z. So d, for example, dr1 can be written as dx1 times dy1 times dz1. So if I want to scale r1 by alpha, it means I have to scale each of x, y, and z by an individual alpha, which means I need 3 alphas for each ri here, which is why the entire alpha to the 3n gets absorbed in here. Now if you're not sure of what I mean by this, take the case for one electron and see what happens. Okay. Alright. Now I also want to make one more change, and this is best seen in Cartesian coordinates. I can write a Laplacian as d squared by dx squared plus d squared by dy squared plus d squared by dz squared. Now what I want to transform these coordinates by alpha, so I want to make it d by d alpha x squared, d by d alpha y squared, d by d alpha z squared, which means I need to multiply and divide by alpha squared. So this alpha squared in the numerator cancels the alpha squared that will appear in the denominator in here. Alright, now we have everything in terms of alpha times ri. So we bring out this extra alpha squared and then make the coordinate transformation. Alpha ri is written as just ri prime, and that leads us to the result we've got here. Now there are many steps I've skipped here. You need to look at those lecture notes and the tutorial, the screencast, to understand what these intervening steps are. In the same way, you can show the second result. And you can also show that for the electron-electron operator, which is given by this repulsive interaction of the electron-electron coordinates, then you get a result like this, that psi alpha of the electron-electron operator, psi alpha, is equal to alpha times psi. Now, what I'd like you to think about is that, in a way, this should have been obvious. Let's forget about matrix elements for the time being. If I wanted to write this operator in terms of the scaled coordinates, I would have to put an alpha in the denominator. Now, to do that, I would need an alpha in the numerator. And this alpha you're seeing here is simply telling you that there's a sort of 1 over r behavior of this operator. Likewise, there's 1 over r behavior of this operator. And the kinetic energy is quadratic in the denominator, so you get an alpha squared. All it's telling you is what is the basic form of the operator in terms of r. Alright, so now we've got these scaling relations, and what we're going to do now is to use a bit of density functional terminology. So we're going to write the kinetic energy, which is a function of the wave function, written like this. And we know that the density determines the Hamiltonian and hence the wave function, so let's write it formally, just formally, as a functional of the density. Likewise, the electron-electron operator, energy, is written formally like this. Okay. Now, how do we justify these as being functionals of the density? It's through the Hohenberg-Kohn theorem, number 1, in fact. So in this notation, the kinetic energy is a functional of the wave function, and it's going to be alpha squared times the kinetic energy. And we can also write this in terms of the density. I should have written it here, but it would be the kinetic energy as a functional of rho alpha is equal to alpha squared times the kinetic energy as a functional of rho. And likewise for the electron-electron energy. Okay, now this is what we need. This is, in fact, for the next derivation, we need this first result in terms of rho and rho alpha and rho. So what we are going to do now, so these scaling relations are exact. There's nothing approximate about them. They are simply formal results based on the mathematical form of these operators. What we're going to do next is approximate. We're going to assume that the kinetic energy as a functional of rho is of the form given here. It's the integral of a function t of rho integrated over all space. And we're going to assume that this function t of rho is a homogeneous function of the density. That is, it's of the form t of x is equal to a x to the b. Now, if you have unsure of what a homogeneous function is, well, go back to your, I think it would have been A level, or, well, just have a look at Riley, Hobson and Benz and search for homogeneous functions. Yeah. But basically a homogeneous function. So let's take some examples. y1 is equal to x squared is homogeneous. There's only a single power of x in there, but y1 is equal to x squared plus x cubed is not homogeneous, because if you scaled x by if you replaced x with alpha x, you couldn't pull out a power of alpha in front of this function y. Alright, so now we have, this is our ansatz, that the kinetic energy is given by this integral of this homogeneous function t of rho. Our job is to find out what this function t of rho is. Now there are just two constants in here, the a in front and the exponent b, which will be a real number. What I'm going to show you is that coordinate scaling can be used to find out what b is, but it cannot be used to find out what a is. Alright, so to find out what a is, we are going to have to use ideas from the free electron gas. Now this is not something I want to do in this course, because you may or may not have had condensed matter B, I think it is. But if you look at the book by Parr and Yang, or pretty much many books on density functional theory, will show you how the uniform electron gas can be used to find out what A is. Okay, so this is what we're going to do. This is our ansatz. I've explained a little bit about homogeneous functions over here, so please have a look. Let's just have a look at it since we are here. T is of the form t of x, which is equal to a times x to the b. The b is a real number, and because it is assumed to be a homogeneous function, we can find b by scaling x. So if we set x is equal to k times x prime, then we will have t of k times x prime is equal to a times kx prime to the power of b. And if you just pull out a k to the b, then we'll get t of x prime back again with a k to the b here. So, you scale the coordinates by k and you will get out a power of k, which tells you exactly what the order of the homogeneous function is in that coordinate, but it won't tell you what a is. So here's how we start. We take the kinetic energy as a function of rho alpha. So that would be the integral, according to our ansatz, of t of rho alpha r dr. But we know that rho alpha r is equal to alpha cubed times rho of alpha r. Where did that come from? That was over here, one of the things I asked you to show, and which was shown in my lectures on coordinate scaling. So let's go back here. So we put in, so now we have the integral of t of alpha cubed rho of alpha r close brackets dr. Okay, now let's multiply and divide by alpha cubed. So we have alpha to the minus 3, and we bring in the alpha cubed in the numerator into this dr. Remember, r is three-dimensional. The integral is in 3 dimensions, so we need 3 alphas here to scale r. Now we change coordinates, set alpha r is equal to r prime, and then drop the prime, and that gives us this line here. So we have an alpha to the minus 3, the integral of t alpha cubed rho r dr. We're going from this step to this step. I have set alpha r is equal to r prime. That makes this dr prime rho of r prime. And since r prime is a dummy coordinate, I'm integrating over all r primes, I can drop the prime to give us rho of r back again. Okay. Now we also know that the kinetic energy of rho of alpha through the scaling relation is alpha squared times the kinetic energy of rho. Therefore, this expression here, which is here, must be equal to alpha squared times the integral of t of rho dr. Okay. Therefore, just comparing the two integrands, we must have t of alpha cubed times rho is equal to alpha to the 5 t of rho. This is how it comes about. Just cross multiply by alpha cubed on both sides, and compare the integrands, and this is what you end up with. And now we change our alpha. We just make alpha prime is equal to alpha cubed. So this becomes t of alpha prime times rho is equal to alpha prime to the 5/3 t of rho, and now we drop the prime to give us t of alpha times rho. So now we have scaled rho by alpha. That's equal to alpha to the 5/3 t of rho. That tells us that t, which is homogeneous, must be homogeneous to a degree 5/3 in rho. That means t is some constant a times rho to the 5/3. Now it can be shown from the uniform electron gas that this constant a, which is generally written as c of f, is given by 3/10 in 3 dimensions, 3 pi squared to the 2/3, or approximately 2.871. So we know what our kinetic energy functional is in this approximation. It's this constant times the integral of rho to the 5/3 integrated over all space. That's it. What were the assumptions we made? We assumed that t is written in the form an integral over a homogeneous function of rho integrated over all space. That was the only assumption. All right. The rest, the scaling relations, the coordinate scaling, that was all mathematically exact. Okay, so now we know what this functional is. What about the electron-electron terms? So we know the kinetic energy part. Well, the electron-electron parts we know from Hartree-Fock theory. There's a Coulomb part, J, and an exchange part, K. We already know that the Coulomb part is written exactly in this form. It's the classical Coulomb energy of an electron density with itself. K. What about K? Well, K is part of the electron-electron energy, so it must also involve. It also involves the operator 1 over r. So they share the same coordinate scaling. K, if K was a functional of a density, then K of the scale density rho of alpha would be alpha times K of rho, exactly the way the electron-electron energy was scaled with alpha. Now, it can be shown then that if you make the same assumption that K now is the integral of a homogeneous function of the density, you can use exactly the same arguments we've used with the kinetic energy to show that K is minus Cx. We don't know what Cx is, but we know it's a negative. There's a negative sign here. Let's get back to that. K is minus Cx times the integral rho to the 4/3 r dr. So this time it's this function K is homogeneous to degree 4/3 in rho. Cx is given by 3/4 of 3 over pi to the 1/3, and once again this constant comes in from the three-dimensional free electron gas. Now, why is there minus sign here? This is quite important. Well, this is the exchange energy. We know that the exchange energy reduces the Coulomb energy. It reduces the Coulomb energy because the exchange energy arises from an antisymmetrization of the wave function, and that keeps electrons of the same spin apart. If they are apart, more often than not, then they have a net reduction in their Coulomb repulsion, and that's why we put a minus sign in here. Now, this is exactly what we saw in Hartree-Fock theory, and in fact this is where this idea has come from. This is due to the exchange hole. Alright. This is just a question for you. I'll leave that as where it is. Please work through these questions as you find them in the lecture notes. Now, if you put that all together, what we have then is that Thomas-Fermi theory. Now, in Thomas-Fermi theory, did not include the exchange term here. It was Dirac who brought it in. Thomas-Fermi theory, you have a kinetic energy part, which is this constant Cf times the integral of rho to the 5/3 over all space, plus the Coulomb part only of the electron-electron term, which is the integral over just the Coulomb self-energy, if you might say, of this density, and then you have the external potential coming in through this last integral. What Dirac does, of course, is to include the exchange term through this integral here. Now, this is as far as what I wanted to show you, but now, if you did want to minimize this, you could minimize this energy functional under the condition that the integral of the density gave you n through a Lagrange multiplier, mu of Tf. You would have to take the functional derivative of this expression with respect to rho. It can be done, and I'd like you to show that you would get this result here. This can be solved, and solving the Thomas-Fermi equations is quite interesting, but it's going to take us away from what we want to do in this course. If you are interested, have a look at chapters 3, where Thomas-Fermi theory is developed, and then chapter 6, where the equations are solved in density functional theory of atoms and molecules by Parr and Yang. The solution to the Thomas-Fermi Dirac equation is given in chapter 6, and as I've said before, all Dirac did was to modify the Thomas-Fermi functional to include the exchange functional K of rho. Now, it turned out that it's not a very good theory. It has some nice results though, but it was a pretty rotten theory because it didn't allow for chemical bonding. So first of all, let's have a look at the nice results, which are taken from Parr and Yang's book, by the way. This is chapter 6, table 6.1 from their book. You have Hartree-Fock energies for a few atoms. These are rare gas atoms from helium going away to the radon, and these are in units of, which are the units they've used here? It's in units of E minus E over Z to the 7/3. I've forgotten why they did that. And this is the modified Thomas-Fermi model. Now the modification was, I'm trying to recall now stuff I have seen a while ago. I believe it was done by Weizsäcker. It's a small modification of what Thomas-Fermi had done. Now what you can see is that for helium, first of all, the results are pretty good. They line up with what you've got from Hartree-Fock theory. The errors are larger for helium, which is a small atom. It's pretty far from a free electron gas, but as you get to the larger of the atoms, you're getting closer and closer. The percentage error is decreasing. So it's not a bad theory, given how little, it was so easy to set up. The problem is here, though. This is a figure from Parr and Yang again. In this thin solid line with wiggles in it, we've got the Hartree-Fock, the r squared weighted Hartree-Fock density, so it's r squared times the density, and that shows you the shell structure of argon quite nicely. You have the 3 shells in here, and the 3 peaks correspond to those 3 shells. What we've got in the sort of various dashed lines and dotted lines are various Thomas-Fermi Dirac models with the Weizsäcker correction, different kinds of corrections. They differ slightly from each other, but they are all wrong. They have the right overall shape, but they do not have the shell structure in them. There are no wiggles. Now what that tells you is that you're never going to have electrons in shells the way you expect them in real atoms. And when you don't get these electrons in these shells, you don't get these Friedel type oscillations in the density, you do not form bonds. So Thomas-Fermi or Thomas-Fermi Dirac theory just does not form bonds, which means it's pretty much useless if you were a chemist, or if you were doing anything other than continuous, homogeneous calculations in physics. And this is why this theory, although it was known, people, everyone assumed that it's just not possible. You cannot form an exact theory based on the density alone. Now it was in this context that Hohenberg and Kohn developed their theorems, because what they have shown in those 2 theorems is that yes, you can, to quote our famous politician here, it is possible to form an exact functional, write the energy as an exact functional of the density. Now that exact functional cannot be the functional Thomas and Fermi put together, but it is in principle possible. You can write an exact functional. The question, of course, is how do you do it? And that leads us on to leads us on to what's now called Kohn-Sham density functional theory. Now, before going to Kohn-Sham density functional theory, I'm going to lead you on to Hartree-Fock theory first. So what we're going to do next, in the next set of lectures, is the lecture set, is look at Hartree-Fock theory as a density functional theory. And we're going to use a number of results from our useful results lecture and lecture notes. So please have a look at those before we get into the next set. And then we're going to see how that all leads us to Kohn-Sham density functional theory. We'll stop here, I think. This is where we stop. Yes, so the next set of topics are going to require a lot of knowledge of functionals. Please revise the work on functionals. And that's the end of this part of the lectures.